To round out this section on the dot product, we're going to talk about an application of the dot product referred to as work. Work is a physical concept that says that if you apply a force to an object and multiply it by the total distance that it travels, then you have yourself work. Now, this does operate under a couple of assumptions. First thing I want to do is talk about units. We've got the SI units, and then we've got hashtag America units. So the force that you'll be applying, if we're going for SI units, that would be newtons, which is a kilogram meter per second squared, or just N. And good old-fashioned America units, that'd be pounds, or for short, olbs. I'm just joshing you. I know why it's like that. Comes from the Libra. Or I just made that up. I don't know. As far as distance is concerned, SI units would be meters, lowercase m. And America, well, then be foots. Now here's the real question. When you multiply a newton times a meter, what do you get? Well, that right there is called a Newton meter. Or a joule. J for short, or NM for Newton meter. In America, take a foot, multiply by a pound, you got yourself a foot-pound. And because we're not as classy as the international system, we don't actually have something classy like that, so we'll just call it foot-pounds. Now, this definition of work that we just gave operates under a couple of assumptions. First one is that the force being applied is a constant force. You're pushing with the same amount of force, or something is pulling with a constant amount of force all the way through it. The other assumption that we're working with is that the force and the distance are in the same direction. Which, honestly, that's usually a good assumption. If you lift something up and you apply a force in an upward direction, it would be really weird to watch that thing go, straight forward, as opposed to coming up. So with that in mind, what we're going to do is take away that second assumption, that the force being applied and the distance are working in the same direction. Just to give you an example of something like that, I have no kids of my own, but sometimes I pick up random kids on the street to do scientific experiments with. So let's say that I have a kid, and the kid is on a sled, because, it's Michigan, and well, for usually about 13 or 14 months out of the year, it's winter here. Now let's say that attached to this sled is a rope. And so attached to that rope is also my hand. So what I do is I start pulling it in this direction. Now, does that mean that the sled is going to suddenly fly into the air? Well, no, unfortunately, it's got gravity working on it. So rather, the displacement is likely going to be along the ground. So despite the fact that my force vector is being pulled in this direction, the displacement vector is going in this direction. So, with that in mind, if a force is going up like this, but the resultant displacement is going like this, what do we do about it? The answer is, well, what we do is we do a vector projection. I only want the component of the force that's acting in the direction of the displacement. So what I would do is I would project this force vector down to the displacement. Now, this is exactly the definition of that projection that we were just working with. So what we're working with is going to be that work is equal to the magnitude of the projection of the force vector onto the displacement vector multiplied by the magnitude of the displacement vector. Now what we're going to do is grab that formula that we had for the projection of one vector onto another, which was the force dotted with the displacement divided by the magnitude of the displacement vector. That's being multiplied by the magnitude of the displacement vector. Boy, do I have some great news there. The magnitudes of the displacement vectors cancel out, and we wind up with the force vector dotted with the displacement vector. Now, we also have several helpful formulas from throughout the section, but something that I do want to point out is that if you happen to know what the angle between them is, then you can also apply this version of the dot product to calculate what your work is. Now do keep in mind, work is a scalar quantity. Work doesn't happen necessarily in a given direction, especially when you have two different vectors working. So, in the context of the word problems that you're going to see, check to see if an angle is given in the problem. If an angle is given, you'll want to use this formula. But if components of the vectors are given, you'll want to stick with just a standard dot product. And, of course, be sure to include units on your final answer. You're multiplying newtons times meters, or you're multiplying feet times pounds, and in either case, you can reference back up top to figure out which version of units you should have on your final answer.